Good morning, students. Here, first I will share my screen with you. Yes. Hello, once again. For chemistry, paper number 11, physical chemistry, we have discussed up till now the introductory part of the elementary quantum mechanics, and in that I have told you classical mechanics, it is related with the macro particles and quantum mechanics, it is related with the micro particles such as electrons. Then we have derived the de-Broglie equation, and that de-Broglie equation, it is equal to lambda, it is equal to h by p, where h is the Planck's constant and p is the momentum of the moving body, and p, it is the product of mass into velocity, and lambda, it is the wave associated with the moving particle, and this is the de-Broglie equation. Then the next point that we have studied, that is the Heisenberg's uncertainty principle, and according to Hygiene, here simultaneous determination of position and momentum, it is not possible for micro particles. That means if we precisely determine the position, we are less accurate in the determination of its momentum and vice versa. This is the short Heisenberg's uncertainty principle. In the derivation of lambda, it is equal to h by p, we have used the two famous equations, and that two famous equations are as according to equation of Einstein's relativity, we have energy associated with mass m, and that energy, it is given by m into c square, and it is equal to the energy associated with one quantum, and that one quantum we call as a h into frequency, where h, it is the Planck's constant again, and f, it is the frequency. Here again we know that frequency, it is equal to a ratio of velocity of light divided by lambda. Therefore, we equate these two famous equations as a equation of Planck's quantum theory, energy associated with one quantum, E, it is equal to h nu, and according to Einstein's theory of relativity, energy associated with mass m, it is given by mc square, and we get this equation mc square, it is equal to hc by lambda. Therefore, we can write mc, it is equal to h by lambda, or lambda, it is equal to h by mc. Then for macroscopic objects, velocity phi can replace the speed of light. Therefore, we have replaced this c, velocity of light, by here velocity phi for microscopic particles, and we have the equation as lambda, it is equal to h upon m into phi, and this h m into phi, it is called as momentum of the particle. Therefore, we can say that the ratio of Planck's constant and momentum, it gives the wavelength of the moving particle. And again remember that the significance of de Broglie equation, it is that for macroscopic particles this lambda is negligible, but in case of microscopic particles this lambda it is greater one and we cannot neglect it. This is the significance of de Broglie hypothesis. Then we have seen the Heisenberg's uncertainty principle, and according to the statement of Heisenberg's uncertainty principle, simultaneous and accurate determination of uh, momentum and position it is not possible, and mathematically delta x into delta p it is greater than or equal to h cross. This is the mathematical expression of Heisenberg's principle. Here delta x it is equal to uncertainty in a position and delta p it is the uncertainty in momentum, and this h cross it has the value h by 2 pi. And this equation states that as we have delta x low, that means if we more precise in the determination of position, we are more uncertain in the determination of its momentum and vice versa. This is the Heisenberg's uncertainty principle. Then this principle it explains the principle of quantum mechanics, and the position and momentum of a particle cannot be accurately measured at the same time. This is the significance of the Heisenberg's uncertainty principle. Here, as already I have told you, delta x, it is the uncertainty in determination of position, and delta p, uncertainty in the determination of momentum, and it is greater than or equal to h by 4 pi. Then if delta x is greater, delta p is less, and if delta p is greater, delta x is less. This is the principle of Heisenberg's. Thus, in such a way, Heisenberg's uncertainty principle introduced the probability approach. That is, we can find the area in a space where probability of finding the electron is more instead of exact location. This is the great achievement of Heisenberg's uncertainty principle. Then we have seen the concept of energy operator, and for your study there is a Hamiltonian operator. You know, the mathematical basis of quantum mechanics requires the concept of operator, and operator it is nothing but any mathematical operation such as differentiation, integration, addition, subtraction, multiplication, division, square root, etc. can be specified by certain symbol known as operator. In short, the mathematical operator it is any function or any rule that converts one function into another function. Then the in classical mechanics, the operator corresponding to total energy of the system is called as Hamiltonian operator, and it is represented as H and putting a cap over the head of the H, and it is called as the Hamiltonian operator. Again, the total energy of the system, it is the sum of kinetic energy of the system and potential energy of the system. And this is written here. The Hamiltonian is the sum of the kinetic energies of all the particles plus the potential energy of the particles associated with the system. The expression of the Hamiltonian operator, it has a different forms. We see here. Then the Hamiltonian operator, it is written as operator H, it is equal to kinetic energy operator plus potential energy operator, and the equivalent equation for the energy can be given as operator H into psi, it is equal to E into psi, where psi, it is a wave function. I will explain you the what is the significance of this psi. Then now, according to classical mechanics, total energy is sum of kinetic energy and potential energy, and we know that kinetic energy, it is equal to 1 half mv square. In terms of momentum, we can write kinetic energy as p square by 2m, where P, it is equal to product of mass into velocity, and the potential energy is a function of coordinates. Therefore, we can write PE, it is equal to phi in a bracket x comma y comma z. These are the coordinates. Then here we can write the total energy in terms of momentum as 1 by 2m in a bracket p x square plus py square plus pz square plus phi in a bracket x comma y comma z, where 1 by 2m into p into x square. This is the momentum along x-axis. This is the momentum along y-axis and momentum along z-axis and potential energy along x-y-z axis. And the corresponding Hamiltonian operator, it is written as 1 by 2m operator px square plus operator py square plus operator pz square plus potential energy operator along x, y, z coordinates. Then the operator along x-axis, it is given by h upon 2 pi I into dou by dou x. Along y-axis, it is given by h upon 2 pi I dou by dou y, and along z-axis, it is given by h upon 2 pi I dou by dou z, and the square of it gives px square, it is equal to product of h upon 2 pi I into dou by dou x into h upon 2 pi I into dou by dou x, and it is equal to minus h square upon 4 pi into dou square by dou x square. Similarly, we can write the operator py square as minus h square upon 4 pi square into dou square by dou y square, and pz square, operator pz square, it is equal to minus h square upon 4 pi square into dou square by dou z square. And here this minus sign, it is for I square, it is equal to minus 1, because I, it is equal to square root of minus 1. Remember. Then, putting these values in the Hamiltonian operator, we have this equation. Operator H, it is equal to minus h square upon 8m pi square in a bracket dou square by dou x square plus dou square by dou y square plus dou square by dou z square plus momentum plus the potential energy along xyz in terms of potential energy operator, and we can write that is h operator, it is equal to minus h square upon 8 pi square m into del square plus potential energy operator along xyz, where del square it is called as Laplacian operator, and del square it has this value. It is written here, del square it is equal to dou square by dou x square plus dou square by dou y square plus dou square by dou z square, and this is called as Laplacian operator. Then putting this value in the total energy, we get this equation. That means the equation H psi it is equal to E psi, where H it is the total energy or Hamiltonian energy, and in terms of Hamiltonian operator we write that equation as H operator into psi it is equal to minus h square upon 8 m pi square in a bracket dou square by dou x square plus dou square by dou y square plus dou square by dou z square bracket complete into psi plus potential energy operator along x y z axis into psi, and this is the general form of Schrodinger equation for stationary waves. Then the today's topic or today's point is the Schrodinger wave equation for electrons. This is the mathematical equation of Schrodinger. Then I will explain you what is the Schrodinger wave equation. The Schrodinger wave equation, it is simply called as Schrodinger equation, and this is the most fundamental equation of quantum physics. Schrodinger wave equation, it is a simply Schrodinger equation, and this is the most fundamental equation of quantum mechanics. This equation is also called as Schrodinger equation, and it is basically a differential equation and widely used in the chemistry and physics to solve the problems based on atomic structure of matter. Schrodinger wave equation describes the behavior of a particle in a field of force or the change of physical quantity over a time, and due to his discovery, this Erwin Schrodinger, who developed the equation and awarded the Nobel Prize in 1933. In short, Schrodinger equation is a wave equation for microscopic particles, and that equation describes the behavior of particle in a field of force or the change of physical quantity over time. It is explained with the help of Schrodinger equation. Then again, in something detail, the Schrodinger equation is also defined as the linear partial differential equation. Schrodinger equation is defined as the linear partial differential equation describing the wave function psi. The equation is named after Erwin Schrodinger using the postulates of quantum mechanics and Schrodinger quantum mechanics and de-Broglie equation. Schrodinger could work on the wave function, and as already explained to you, the wave function means what? Here listen carefully. What is wave function? Here in quantum physics, a wave function is a mathematical description of a quantum state of a particle. Wave function is a mathematical description of a quantum state of particle as a function of momentum, time, position and spin. The symbol used for a wave function is a Greek letter called psi, and it is represented as this. This is a psi known as wave function. I repeat once again, wave function is mathematical description of a quantum state of particle as a function of momentum, time, position and spin, and the symbol of the wave function is a Greek letter psi. By using a wave function, the probability of finding an electron within the matter wave can be explained. This can be obtained by including an imaginary number that is squared to get a real number solution resulting in the position of an electron. The concept of wave function was introduced in the year 1925 and with the help of Schrodinger equation. Then all of you are very well known regarding the Bohr's atomic structure, and these are the certain specific orbit radii. For n equal to 1, n it is the principal quantum number. As the number of n increases, the radius it goes on increasing, and this when the electron it jumps from higher energy to lower energy, we have the line spectrum, and this is the this diagram. It shows the quantization of energy. As the Bohr's atomic model, it explains well the atomic spectrum for one electron system, and it fails to explain the multi-electron system. So here the Bohr model failed to predict the emission lines for multi-electron atoms, and due to this failure a scientist introduced a new physics, and that new physics branch it is the quantum mechanics. In short, quantum mechanics it is applied to the multi-electron system also. Then again, this is the uncertainty principle that we recall as the position and momentum of particle cannot be simultaneously determined to arbitrarily high precision. Thus, the in this way, quantum theory reminds us, as behavior has put it, of the world wisdom that when searching for harmony in life, one must never forget that in the drama of existence, we are ourselves both players and spectators. This is the famous quote written by the scientist Heisenberg in his research paper. I will repeat once again. Heisenberg thought that quantum theory reminds us, as Bohr has put it, the world wisdom that when searching for harmony in life, one must never forget that in the drama of existence, we are ourselves both players and spectators. Sorry. It is understandable that in our scientific relation to nature, our own activity becomes very important when we have to deal with parts of nature. Sorry, I will repeat. It is understandable that in our scientific relation to nature, our own activity becomes very important when we have to deal with parts of nature into which we can penetrate only by using the most elaborate tools. This is the famous quotation written by Heisenberg. Then, Schrodinger compared the electron wave as a standing wave, and the standing wave, it is the wave associated with stretched string, or standing wave, it is compared as a motion of a stretched string, and this is the unplucked string. That means it has no any kind of motion. But if we have given a stroke to this stretched string, then we have nodes and antinodes, and here it is given a half wavelength. Here it is a two half wavelengths. Here there are three half wavelengths, four half wavelengths. Then Erwin Schrodinger in 1926 wrote a wave equation and is known as Schrodinger Equation. The electron as a standing wave bound to nucleus. He used a classical wave equation and de-Broglie relationship of a wave-particle duality and obtained a wave equation for the electron in the atom. I will repeat once again. In the derivation of Schrodinger wave equation, here he considered electron as a standing wave bound to the nucleus. He used the classical wave equation and de Broglie relationship of a wave-particle duality and obtained a wave equation for the electron in the atom. Here, suppose we have hydrogen atom, and all of you know that in the hydrogen atom at the center there is a nucleus, and around the nucleus electron it revolves in a circular orbit. Suppose this electron it has a charge minus E, and it is free to move around the electric field of fixed proton of charge plus E. And remember that proton is approximately 2000 times heavier than electron. So we consider it is fixed, and the electron has a potential energy due to attraction of proton, and the potential energy it is given by the equation minus E square upon 4 pi epsilon 0 into R, where R is the electron-proton separation. The electron has a kinetic energy and it is equal to 1 half mv square. In terms of momentum, it is given by the equation p square by 2m. Therefore, total energy of the electron it is given by p square upon 2m minus e square upon 4 pi epsilon 0 into r, where epsilon it is the dielectric constant. Then just imagine the thoughts of new scientists, and here for you there is a ultimate quantum puzzle. Suppose you have asked, does the universe exist when nobody is looking? What is your answer? I repeat the question. Does the universe exist when nobody is looking? What is your answer? Your answer is no. If there is nobody for looking, how we can say that there is a universe? And these are the thoughts of new science. Then the standing wave it is given by the equation psi it is equal to psi 0 sine 2 pi nu t. where psi 0 it is the amplitude, and if we replace omega it is equal to 2 pi nu, and psi 0 it is the amplitude and nu is a frequency, and differentiating this equation we get these equations we see later on. Then this is the Schrodinger equation in a spherical coordinates we see later on, and the next point of your study it is the quantum numbers. Then for today's lecture we will see the detailed derivation of a Schrodinger equation. Schrodinger used a standing wave and de-Broglie's equation to formulate his equation. Thank you for your patient listening. Thank you very much.